Hi, this is Tim Shu from San Jose State University, and I'm here to present a brief list of algebraic functions. It's really just a list, as I'll explain in a minute. The disclaimer that I should start with is that this video is really meant only as a review, or really just a list of functions with which you should be familiar from pre-calculus or even previous courses. There isn't really enough information here for you to learn from scratch what you'll need to know later. So if you've never seen this stuff before, if you've never seen these functions before, please review this material in your favorite pre-calculus textbook or ask your teacher for extra help. All right, so now having talked about what this video is not going to do, let's get to it with linear functions. So a linear function, as I hope you all know, has the form f of x equals mx plus b for some constants m and b. So graphically, what do these constants m and b mean? M is the slope of the line y equals f of x, which is mx plus b, and b is the y-intercept of that line. So I'm going to take the opportunity here to remind you of a key formula. It's really important for calculus. The point-slope formula of the equation of the line through the point a comma b with slope m is, I hope you remember this, y minus b is equal to m times x minus a. There it is again. Y minus b is equal to m times x minus a. The point-slope formula is critical for calculus. It's really important for calculus because one of the things that comes up all the time in calculus is that you'll need to find the equation of a line where you know its slope and a point through which it passes. And what can you do with that? Yes, you apply the point-slope formula because the input to the point-slope formula is a point and a slope. Thus the name. There we go. All right, moving on. The power function. So a power function has the form f of x equals x to the a for some constant a. And in particular, we'll be interested in the following cases most often. F of x equals x to the n, where n is a positive integer. F of x equals x to the 1 over n for an integer n over 2. And if you don't remember what 1 over n means, so x to the 1/2, it really means the square root of x. So I'm really saying f of x equals square root of x, cube root of x, fourth root of x, and so on. So those are particularly interesting cases of power functions. And f of x equals x to the minus n for a positive integer n. And what do I really mean by that? Well, if you remember what negative exponents mean, I really mean f of x equals 1 over x squared, 1 over x cubed, and so on. So here's some pictures of power functions. So if f of x equals x to the n, where n is a positive even integer, that looks like a smiley face, as you can see here. So here's x squared, x to the 4th, and x to the 6th, and as you can see, as the exponent n increases, you get a more dramatic increase for greater n. Though note that x to the 6th is actually below x to the 4th, this is below x squared for small values of x, but when you have big values of x, so here we go from 2 to 2, really you can sort of tell that x to the 6th crushes x to the 4th, which in turn crushes x squared. And it gets more dramatic as you get farther out from the origin. All right, so that's what happens for when n is even. When n is an odd positive integer, you get a graph, you look at the corresponding power function as a graph that goes up on the right and down on the left. So here's x cubed, x to the 5th, x to the 7th, and as you can see, as your exponent increases, you get more dramatic increase for greater n. So over here you can see that for small values of x, you can see that x cubed is greater than x to the 7th. But for any reasonably large values of x, you can see x to the 7th is way bigger than x cubed. All right, now turning to those root functions. So when n is an even positive integer, this is the squared function, fourth root function, sixth root function. You get functions that look like graphs that look like this, and those only work for non-negative x greater than or equal to 0. So here you get f of x equals square root of x, fourth root of x, sixth root of x. But for odd positive integers, if you take third root, fifth roots, and seventh roots, you get functions that are defined for all real x. So that just in case you're wondering, this is a strange computer code for cube root, fifth root, and seventh root. Anyway, once again, here is the cube root of x, fifth root of x, seventh root of x, and there we go. So moving now on now to negative exponents. So if n is a positive odd integer, and you look at x to the minus n, that is 1 over x cubed, 1 over x to the 5th, you can see that you get a function that blows up on both sides of x equals 0. It blows up to positive infinity on the right side and negative infinity on the left. So here's 1 over x, 1 over x cubed, 1 over x to the 5th. So this blow up is more dramatic for larger exponents. And in a similar way, for f of x equals x to the minus n, where n is a positive even integer, you get something that blows up to plus infinity on both sides of x equals 0. And again, this blow up is more dramatic for larger exponents. So here's 1 over x squared, 1 over x to the fourth. This blow up is so dramatic. Sorry, this blow up over here is so dramatic you can't even really see it. But that's 1 over x to the sixth. All right, turning now to polynomial functions. A polynomial function has the form p of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a bunch of other things all the way down to a2 times x squared plus a1 times x to the 1, which is really just x, plus a0 times x to the 0, which is just a0, where these a's, the an, n minus 1, and so on, are real constants. So assuming that an is not equal to 0, and then I haven't written this out in some silly way, because if an were 0, I could just erase this and write it with less effort, then this positive integer n is called the degree of p of x. A sub n is called the leading coefficient of p of x. A sub n x to the n is called the leading term of p of x. So this number by itself is the leading coefficient, but if you include the x to the n, that's the leading term. And then the last term over here, the a sub 0, is called the constant term of p of x. And to see what the graph of a polynomial function looks like, well, it's about not easy to predict. So here's one x to the fifth minus 20x cubed plus 115x plus 136. And what is this going to look like? I have to say, if I hadn't sort of worked out this example beforehand, I would have no idea. But here's what it looks like. It's bumpy. And look, and this happens to be a fifth degree polynomial with 1, 2, 3, 4 bumps. In fact, we'll explain in this course why there cannot be more than 4 of those bumps. In general, you sort of expect there to be 4 bumps. Bump, 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 bump. And it is, in fact, a standard calculus problem to locate these bumps in a polynomial graph precisely. So, in principle, at least, even though the calculations can be kind of gnarly, one of the things we learn how to do in this class is to figure out what the coordinates of these points are. Okay, turning to rational functions. A rational function is the quotient of 2 polynomial functions, p of x over q of x. So for example, here's a rational function, f of x equals x cubed minus x plus 1, that's a polynomial, and x squared plus 25x cubed minus 3x plus 7, that's also a polynomial, and so their ratio is a rational function. And here is sort of what a graph of a sort of random rational function will look like. So these are even harder to predict. So here's x cubed plus 17x over x to the fifth minus 20x cubed plus 115x plus 1. So really, I'd have no idea what this thing was if I hadn't worked it out already. And so here it goes. Well, and actually, this is a pretty interesting one because this one looks like it looks just like a two-hung graph, but there's something mysterious happening in the middle here, between right around x equals 0. So let's zoom in and see what that looks like. So if you look at x between minus 1 and 1, you can see a little bit better that that your function seems to blow up there and to plus infinity, go down there to minus infinity, and actually. This looks so interesting. Let's look even closer. If you look even closer, you'll see that the function not only blows up to positive infinity, it's not actually at 0. It's like just before x equals 0. It goes down to negative infinity over here. So again, using calculus, you can get a very good qualitative picture of what the graph of this rational function looks like, at least in theory, because the calculations are indeed quite gnarly, as people of my generation used to say. But from calculus, for example, you can sort of deduce that there is a valley here. There's actually a bottom here to this graph somewhere. All right, so now turning to the most general case, the sort of generalization of everything we've seen, any function obtained by repeatedly applying plus and minus and times and divides and nth powers and nth roots to x's and constants is called an algebraic function. And just to give a totally random example, f of x equals x plus the square root of 1 minus x cubed all over x minus the square root of 1 plus x cubed. So this is like a totally randomly made function that has no particular significance, at least to me. But this is just a random example of an algebraic function. And yeah, so you'll see stuff like that in this course. All right, so what other functions are there, just in case you haven't seen these things, or if you don't remember them? The thing is, some of the most important examples of functions in calculus cannot be expressed just in terms of algebra, and these include the exponential functions, a to the x, where a is positive, the log functions, the log of x to the base a, where a is usually greater than 1, the trigonometric functions, sine, cosine, tangent, cotangent, secant, and cosecant, and the inverse trig functions, especially arcsine, or inverse sine of x, or arctan equals inverse tangent of x, and so on. Those will happen later, you'll see. All right, that's enough for now. Go do something useful. Bye!